You know, when I think about it, the most deceptive thing in my house is probably that little white charger plugged into my wall.
Right.
I just plug in my phone, I hear that little ding, the battery icon turns green, and I don't think about it again. It just works. It feels like filling a glass of water.
Uh-huh. It's the ultimate magic trick of modern tech, isn't it? We see this smooth, simple animation, and we just assume the process behind it is simple.
It's not. I've been looking at the actual schematics, the blueprints for the iPhone 15 series, and honestly, it's kind of terrifying. It's not filling a tank at all. It's like managing a national power grid inside a little glass box.
That's a perfect analogy. Behind that one little battery icon is this sprawling, chaotic highway system of power management that has to make thousands of decisions a second. And with the iPhone 15, especially the Pro models, that whole highway system got a complete architectural renovation that most of us will never even see.
And that is exactly what we're going to do in this deep dive. We're going to try and strip away the glass and the marketing and really look at that invisible architecture. We're going to talk about why your phone is a sandwich.
Yeah, the sandwich.
We're going to talk about a chip with a, frankly, awesome name, the Rubicon. And we're going to unpack this massive design change that separates the standard 15 from the Pro.
And we're doing this by looking at the actual board diagrams. The technical term is bitmaps, and the repair schematics. It's really the difference between looking at a tourist map of a city and, you know, the blueprints for the electrical grid running under the streets.
Okay, so let's start at the very beginning, the foundation. When we say logic board singular, we're already kind of lying, aren't we? It hasn't been just one board for a while now.
Right. It's a sandwich. It's been that way since the iPhone X, really. It all comes down to a physics problem. You want a huge battery, but you also want a tiny phone. So Apple's solution was to split the motherboard into two slices, a top and a bottom PCB, and just stack them.
Which saves a ton of space.
Yeah.
But you can't just glue two circuit boards together. They have to communicate. The brain on the top has to talk to the modem on the bottom.
And that's the real engineering challenge. They use something called an interposer frame. The easiest way to think about it is like a layer of jam between two slices of bread.
Okay.
Except instead of jam, it's a frame with hundreds of tiny, tiny little solder balls that act as connection points.
So this is where that visualization you mentioned comes in. If I'm a repair tech and I just plop the screen off, I'm just seeing the top, the ground view, let's call it. I see chips, shields, connectors, but I don't see the logic.
Exactly. You're standing on the ground, so you can't see the traffic patterns because all the buildings are in your way. To see the logic, you have to look at the schematic. That's like sending up a drone.
The drone view.
All of a sudden, you have this top-down view. You see the roads. You can see that one copper trace starts at the battery connector. It dives under a shield. It crosses that interposer bridge.
And ends up on a chip on the bottom board you couldn't even see before.
Precisely. The drone view reveals the connections that the physical view completely hides.
Okay, so let's take that drone and follow the power. I plug in my USB-C cable. Power hits the phone. So who answers the door?
The gatekeeper. There is one specific integrated circuit, an IC, that handles that initial input. And I have to say, the engineers have some fun with the internal code names for this chip.
It's a theme, isn't it? A river theme.
It is, yeah. A few years ago, back in the iPhone 6 days, the charger chip was called Tigris. Then it evolved, became Yangtze, and now in the iPhone 15 series, the schematic labels chip U4000 as Rubicon.
The Rubicon. That sounds a little ominous. You know, crossing the Rubicon. Point of no return.
It's perfect, though, because this chip manages that critical handoff. It takes the raw voltage from the charger, the VBUS line, and it has to decide where it all goes. It's the switchboard. It says, okay, 2 amps go charge the battery, 1 amp goes to the system to keep the lights on. It really is the point of no return for power entering the phone.
So if the Rubicon dies, say, I use a cheap gas station cable, and it sends a voltage spike that fries it, the phone is just a brick.
Total brick. Doesn't matter if your battery is at 100%. If Rubicon is dead, the system has no idea how to distribute power. The main gate is just closed.
Okay, so Rubicon manages the input, but this is where the schematics get really, really interesting, and where that drone view showed me something I completely didn't expect. I think most people, myself included, just assume the iPhone 15 and the 15 Pro are basically the same phone inside.
Yeah, that's a common thought.
You know, maybe the Pro has a better camera, faster chip, but the basic layout, probably identical.
And that assumption is just dead wrong. If you look at the board layouts side by side, the architecture is fundamentally different. It's not just a spec bump, it's a totally different design philosophy.
Let's call that the core hardware split. Can you break that down for us?
Sure. So the standard 15 and 15 Plus are running on the A16 chip. It's basically using the board architecture from last year's iPhone 14 Pro. But the 15 Pro and Pro Max are on the new A17 Pro chip.
Right.
And because that A17 draws power so differently and has different thermal needs, the engineers basically had to move all the furniture in the room.
So let's start with something simple, the battery connector itself. On the standard 15, looking at the diagram, it's a 3-pin connector. Looks pretty standard.
Correct. You've got your positive, your negative, and a data line. Simple. Tried and true. But now look at the 15 Pro schematic.
Whoa, okay, that's a 5-pin connector.
Yeah.
And the name of the battery line is different. It's not just PPVA TVCC anymore. Now it's PPBA TVCC CVC BPIC.
BPIC.
That definitely sounds like a new acronym, a new component.
It is. It stands for Battery Protection IC. It's a dedicated chip U4200 on the board that sits as a middleman between the battery itself and the rest of the phone.
So wait, why does the Pro need a bodyguard for its battery, but the standard 15 doesn't? Is the A17 chip that more demanding?
Demanding is exactly the right word. It's not that it's dangerous. It's that all the Pro features, the high refresh rate screen, the A17's peak performance, they require incredibly tight power tolerances. So this BPIC allows for much more granular monitoring. It's checking the current with way more precision. It's just an extra layer of telemetry.
So the standard 15 is flying by sight, and the Pro is flying on instruments.
That is a fantastic way to put it. But the biggest change, and this is the part that really makes you appreciate the physics of it all, is where they put these key chips. This is where that whole sandwich design really comes into play.
The furniture moving. Okay, walk us through it.
Right. Picture the sandwich again. Top board, bottom board, interposer in the middle. In the standard iPhone 15, the battery connects on the top board, but the heavy power chips, like our friend Rubicon, and the main power management unit, the PMU, they're often on the other side of the sandwich.
So the power has to travel.
It has to cross the bridge. You are pushing all that raw battery power, all that amperage, through those tiny little solder joints on the interposer just to get to the chips that need to distribute it.
And every time you make electricity cross a bridge like that, from a physics standpoint, you're adding a resistance, aren't you?
You're adding resistance, which creates heat. But even more importantly, you're adding a mechanical point of failure. That interposer is the weakest part of the whole phone. If you drop it hard, the layers can separate. And if the main power line is crossing that bridge and the bridge breaks...
Lights out.
Exactly. You've just severed the main artery.
So how did they fix this on the Pro?
On the 15 Pro, the engineers moved everything to the same side of the street. The battery connector, the Rubicon charger chip, and the main PMU are all neighbors, all on the top board.
So the heavy trucks don't have to cross the fragile bridge anymore.
Yeah.
They stay on the main highway.
Precisely. The entire high current loop is contained on one solid piece of fiberglass. The only things crossing that interposer on the Pro are like data lines and test points, light traffic. From a design perspective, it is a massive durability upgrade.
That's fascinating. Just by rearranging the layout, they made the phone inherently more resistant to drop damage, electrically speaking.
Yes. But, and there's always a but, in engineering it adds complexity. Now you have that BPIC chip we mentioned. So if something goes wrong with the power reading, you have another potential culprit. It's not just, is the battery bad? Now it's, is the battery bad, or is the bodyguard lying to me?
Which actually brings us to a really critical point. How does the phone even know if the battery's bad? Or even just how much battery is left? We just see 42% in the corner and take it as fact. But you can't just look in an electricity tank.
No, you can't. And this is one of my favorite parts of the schematic. They literally call it the gas gauge protocol.
Literally gas.
Yep. The data lines are labeled ITC gas gauge. But to make that gauge work, the phone relies on a component that's smaller than a grain of sand. It's called the sense resistor, or R-sense.
I've seen those on the diagrams. They look like nothing, just a tiny black speck. If I sneezed, it would be gone forever.
But that little speck is a precision instrument. It has a resistance of something like 0.0003 ohms.
0.003, that's basically zero. Why is it even there?
Because basically zero isn't actually zero, and that is the whole key. Imagine you have a pipe with water flowing through it. If you put a tiny restriction in that pipe, the pressure is going to drop just a little bit right after that restriction.
Okay, yeah. Basic fluid dynamics.
Right. The sense resistor is that restriction for electricity. When current flows through it, there's a microscopic voltage drop. The PMU measures that drop. And because it knows the resistance is exactly 0.0003 ohms, it can use Ohm's law to calculate precisely how many milliamps are flowing.
So it's a turnstile. It's counting every person going into the subway.
That is the perfect analogy. It counts every electron leaving the battery and every electron coming back in from the charger. That is how it knows you're at 42%. It's all just math.
But that sounds incredibly fragile. You mentioned these things are delicate.
Extremely. Let's say you drop your phone. Or maybe a technician is doing a screen repair and they heat the board a little too much near that resistor. The solder can crack, or the material itself can stretch just a tiny bit.
And if it stretches, its resistance changes.
Exactly. Let's say it goes from 0.0003 ohms all the way up to 1 ohm. To us, 1 ohm is nothing. But to the phone circuitry, that's a canyon.
The math breaks.
The math completely shatters. All of a sudden, the phone sees this massive voltage drop and it thinks, oh my God, there are 100 amps flowing. The battery must be exploding.
And what does it do?
It panics. It pulls the plug. It shuts down immediately to save itself.
Is that what causes those weird restart loops you sometimes hear about, where a fan will just turn on and then off every 3 minutes?
That's very often a classic panic log. The phone boots, the gas gauge, takes a reading, sees impossible numbers, and just forces a restart. All because a component the size of a dust mite got bent out of shape.
Wow. That is wild. It just highlights how this whole system is really walking on a physical tightrope.
It really is. And that fragility leads to one other key concept from the schematics. We always say the phone runs off the battery, but if you look at the power flow in these documents, that's not technically true, is it?
Yeah, I saw this. I see the main battery line, VBA, going into all the chips, but then there's this other line coming out.
Right. Think about a battery. It's messy. When it's full, it might be putting out 4.3 volts. When it's nearly dead, it might be 3.0 volts. It's always fluctuating.
And computer chips hate fluctuation.
They absolutely despise it. If you fed that raw, messy battery power straight into the A17 chip, it would crash or burn out in a millisecond. It needs a steady, stable source.
That's where the Rubicon and the PMU come in again?
Exactly. They act like a refinery. They take that crude variable VBIC power from the battery and they regulate it into a perfectly stable, unmoving voltage rail. On the iPhone schematics, this is called VDD main.
VDD main. Yeah, that label is everywhere on this map. It goes to the audio chips, Face ID, the cameras, everything.
It's the lifeblood. Your phone actually runs on VDD main. The battery is just the crude oil reservoir. VDD main is the refined gasoline that makes the engine turn over.
So if the Rubicon chip, the refinery breaks, it doesn't matter how much oil is in the tank.
Correct. You can have a 100% charged battery, but if that conversion to VDD main fails, the CPU gets no power. The screen gets no power. The phone is dead.
It really changes how you think about a dead phone. It's almost never just the battery is bad. It could be the Rubicon, it could be the sense resistor, it could be a tiny crack in that interposer bridge.
That's the reality of modern electronics repair. We're building systems that are incredibly dense and efficient, like moving all those chips to one side on the Pro, but that same density pushes the limits of what a human can physically repair.
And that feels like the big takeaway here. The so what? The iPhone 15 Pro is objectively a better engineered device. The layout is more durable, but it also feels like we're getting closer and closer to a black box that we can't actually fix.
We're absolutely operating at the limits of human vision and dexterity. When a loose connection on a buried layer or a resistor value drifting by a fraction of an ohm can kill a $1,000 device, the skill needed to diagnose that goes through the roof.
It's not just swapping parts anymore, it's microsurgery.
It is. I think we're reaching a point where the logic board is designed by algorithms, and maybe it can only be reliably fixed by robots or, not fixed at all.
Well, until the robots take over the repair shops, I guess at least we have the drone view to help us understand the city.
And the schematics to help us read the street signs.
I hope this deep dive helped you visualize what is actually happening in your pocket. So next time you plug your phone in and hear that little ding, maybe spare a thought for the Rubicon chip working overtime to keep the lights on. Thanks for listening.
Stay curious.
Every single time you tap your iPhone, swipe a photo, or just plug it into charge, there's this secret journey taking place inside. It's a super complex, high-speed trip that happens, millions of times a day, and we never even see it. So today, we're going to follow that journey step by step and really get a feel for the incredible engineering that's powering that device in your pocket. Let's start the tour. Okay, at first glance, I know what you're thinking. This looks like some kind of chaotic city map or maybe a subway system diagram. But this is our roadmap. It's the power distribution network inside an iPhone 15. And our tour is going to start exactly where all the energy begins, right at the battery connector. You can think of it as the main power station for this entire little metropolis. So the second that power leaves the battery, it jumps onto a main power line, which is basically a superhighway for electricity called PP_BAT_VCC. Think of it as the main artery, the absolute starting point for everything your phone does. But here's the problem. How do you route a massive superhighway inside a device that has to fit in the palm of your hand? Yeah, to fit more and more stuff, we're talking bigger cameras, more sensors, larger batteries, into a device this thin, engineers had to get really creative. They couldn't build outwards, so they had to build up. And this led to a design choice that is, well, it's brilliant, but it's also incredibly complex. That's right. The main logic board in modern iPhones isn't one flat piece anymore. It's actually two separate circuit boards stacked right on top of each other. Now, this stacked design saves a ton of space, but it also creates a brand new problem. How do you get power and all that data from one slice of bread to the other? What they needed was a bridge. And solution is this little engineering marvel called the interposer. It's the critical link that makes this whole stack design even possible. Seriously, without this bridge, the two halves of the phone's brain couldn't talk to each other, and not a single drop of power could flow between them. So this is the interposer. It's a really sophisticated, multi-layered connector with hundreds of tiny little contact points. You can't think of it like a simple plug. It's more like a high-density, multi-lane bridge that connects the power highways and all the data lanes from the top board directly to the bottom one. Now, what's really fascinating here is just the sheer complexity of it. On the left, that's the technical schematic, the blueprint for all those connections. And on the right, you can see the actual physical pads on the board. See how many of them are dedicated to that main PP-BATT-VCC power line? There's a good reason for that. Just like your house needs a thick main cable to handle all the electricity, the iPhone needs a bunch of connection points to safely handle all the current coming from that battery. Okay, so the power has successfully crossed the bridge, but it can't just flow everywhere all at once. That would just be chaos, right? It needs to be managed. It needs to be directed and converted with incredible precision. And this is where a group of really smart chips, the integrated circuits, come into play. Let's call them the traffic cops of this entire power grid. Our first traffic cop is the U4000 chip, and its codename is Rubicon. This is the master charging IC. So when you plug your phone in, Rubicon is the one managing the power coming from the charger, sending it to safely charge the battery, and it also helps regulate the power coming out of the battery to the rest of the phone. It's basically the main gatekeeper. Now, from the gatekeeper, we move to the absolute brain of the operation, the U3300, or what we call the Power Management Unit, the PMU. The PMU is incredible. It takes that raw power from the battery, and it creates all the different super precise voltages needed for every single component, from the beastly A17 Pro CPU all the way down to the tiny chip that runs your screen. It is the master controller. So far, this whole journey we've been on applies to the standard iPhone 15. But what about the Pro models? I mean, what gives them the Pro name? Well, it turns out part of the answer lies in an extra layer of security, right at the very beginning of our power journey. This slide lays it out perfectly. In the standard iPhone 15, power goes from the battery right to that main charging IC. But in the iPhone 15 Pro, there's an extra step. Power first has to go through a dedicated battery protection IC, or BPIC. You can think of it as an exclusive bodyguard. And this chip right here, the U4200, is that bodyguard. It acts as the very first line of defense. It gives the phone an extra layer of monitoring and protection for the battery right at the source. It's one of those subtle but really important engineering differences that just adds that extra bit of robustness to the more expensive Pro lineup. So let's take a step back. We've traveled from the battery, we've crossed a bridge between two stacked boards, and we've met the traffic cops that direct the whole flow of energy. It's this incredibly complex dance of components that's all happening in a space that's smaller than a postage stamp. It's just wild. So, what are the big takeaways from our little tour? Well, first, that super compact design is only possible because of those stacked boards. Second, that whole stack is held together by that critical bridge, the interposer. Third,
All that power is being carefully managed by a whole team of intelligent traffic cop chips. And finally, the Pro models, they get an extra bodyguard chip for even more robust protection.
The next time you pick up your phone, just take a second and remember this hidden world we just explored. Behind that simple, elegant piece of glass is this bustling metropolis of power highways, bridges, and controllers, all working in perfect harmony. And just think, the simplest hop on your screen is what sets this entire incredible journey into motion.